Today we're going to talk about routing concepts, talk about our different routing protocols. So far we've talked about switches, and now we're going to talk a little bit about our routers. So far with our switches, a few things you need to keep in mind is that the Ethernet switches functioned at the data link layer, layer 2, and are used to forward Ethernet frames between devices within the same network. Our routers transfer information between networks. So our switches work within the same network. Our routers move information between networks. So basically a router connects one network to another network, and it's responsible for the delivery of the packets across different networks. The destination of the IP packet must be a web server in another, may be a web server in another country, or an email server in the same building. But if it's in a different network based off of your IP addresses, it has to go through those routers. The routers build what's called a routing table, and they use this routing table to determine the best path to use to forward the packet. And it's the responsibility of the routers to deliver those packets in a timely manner. You don't want your information sitting out there and not going where it needs to go, because the routers will drop that information if it takes too long. The effectiveness of your inter-network communication depends to a large degree on the ability of routers to forward packets in the most efficient way possible. So as we go over routers, some of the things you need to pay close attention to and you need to pick up on are: we're going to configure a router to route between multiple directly connected networks. You need to be able to describe the primary functions and features of a router. Explain how routers use information in data packets to make forwarding decisions in a small and medium-sized business network. Explain the encapsulation and de-encapsulation process used by routers when switching packets between interfaces. We're going to compare ways in which a router builds a routing table when operating in a small to medium-sized business network. We're going to explain routing table entries for directly connected networks. Those are the ones who are plugged directly into your routers. And explain how a router builds a routing table of directly connected networks. We'll also explain how a router builds a routing table using static routes and how it builds a routing table using dynamic routing protocols. Let's begin by looking at the characteristics of a network. Our network characteristics include the topology, and these are the physical and logical topologies. Remember that the physical topology is the arrangement of the cables, the network devices, and any end devices. It describes how the network devices are actually interconnected with the wires and with cables. Your logical topology is the path over which the data is transferred in a network, and it describes how the network devices appear connected to network users. Next, we have speed, and speed is measured by the data rate in bits per second of a given link in the network, and you'll see that by B/S bits per second. Next, we have cost, and cost indicates the general expense of purchasing of network components and installation and maintenance of the network. So you have to take into account how much money is it going to take to do this. Next, we have security. And security indicates how protected the network is, including the information that's transmitted over the network. The subject of security is important, so you have to keep in mind, how well am I going to keep the information that's being transmitted over my network safe? How easy is it for someone to get onto my network and get the information that's there? Next, we have availability, and it measures the probability of the network is available for use when it's required. So if you want your system to always be available, you're wanting 24/7 availability, you need to make sure you have measures in place to allow that to happen. Next, we have scalability, and that indicates how easy the network can accommodate more users? Can you put more users on it? Can you put more devices on it? How well does it scale to increase, or how well does it scale if you need to decrease? You have reliability. That indicates the dependability of the components that make up your network. How dependable are your routers, your switches, your PCs, your servers? And it's often measured as a probability of failure or the mean time between failures. So these are the characteristics and attributes that provides a means for us to be able to compare different networking solutions, so we can look and see what do you really need when you develop your network. So why routing? Basically, the router is responsible for the traffic going between your different networks, so the router is very necessary. It is how we communicate between the two, and without the router determining best path to the destination and forwarding the traffic to the next router along the path, your information wouldn't get anywhere. The router is responsible for the routing of traffic, like I said, between your networks. On this particular example here, I have two PCs, I have two switches, and I have my router. I've done show IP route as my command on my router, and it's showing me the two routes that are connected to my router. So 192.168.1.20/24, so it's a 24-bit network. It's directly connected to Fast Ethernet 000, as you see here by this illustration. And then I have 192.168.2.0/24, so a different 24-bit network is directly connected to the serial interface. So this is one way that we can see what routes are available on our router. We can do the show command. So this one is show IP routes. Now let's look a little bit more at our routers. The routers are computers. Routers are specialized computers that have a particular function, and they contain the central processing unit. They have an operating system, or OS, and the routers that we use are using the Cisco IOS. Memory and storage, we have several different types. We have RAM, ROM, NVRAM, flash, and hard drive. So for RAM, it's volatile, just like it is on your PC or your laptop. It's running the iOS, it's running the configuration file, it has your IP routing and your ARP tables, and it does your packet buffers. Next we have ROM. ROM is non-volatile, so that means it doesn't disappear. It has your boot up instructions, it has basic diagnostic software, and it has a very limited iOS on it. Next you have your NVRAM. It's non-volatile and it has your startup configuration file. Finally, we have our flash. It's non-volatile, it has the iOS, it has other system files, and the iOS is copied from flash into RAM during the boot up process. And like I said, it is non-volatile. It does not lose its contents when it's powered off. Some of the things you do need to take note of with the router that's a little bit different than your computer is that the router does not have video adapters or sound card adapters. So instead it's just specialized just for the ports that are on it. So routers use these special ports and network interface cards to interconnect to other network devices. Here's the back of this particular router. It has two 4 gig flash card slots because you put the flash cards in that have the non-volatile iOS on them, correct? This one has a double wide slot that allows you to put other information in. This one has a console USB mini, it has a console RJ45, and a USB ports. We also have our LAN interfaces. Our routers interconnect our networks. So routers can connect multiple networks. That means one or more networks to that additional router. Routers have multiple interfaces, each on a different IP network. Our primary functions of our routers are two things. It's going to determine the best path to send packets, and it's going to forward packets towards their destination, because that's its job, is to transmit information from one network to the other. To determine the best path to send packets, it's going to use its routing table to determine that path, and that routing table is built as the router learns the different networks. It's going to forward packets towards their destination, and these forwarded packets to the interface indicated in your routing table. So depending on which interface holds that network or its next hop, it's going to go through that interface. It encapsulates the packet and forwards it out towards its destination. Routers can use static routes and dynamic routing protocols to learn about remote networks and to build their routing tables. You'll see in this example here how the router chooses its best path. We have a PC on the LAN network 192.168.1.0 that is sending information to the network 192.168.2.0. So the information goes from the device through the switch to our router. Here we've done a show IP route for the router so that you can see the routing table, and you'll see that this particular router has two directly connected networks. One is through the fast Ethernet port 00, the other through the serial interface 000, and one is connected, has a static route to 192.168.3.0/24, so it also is a 24-bit network. So what this is going to do now is it's going to take that packet, because it's in its routing table and it knows which interface to send the 192.168.2.0 packet to. So we know that the router is going to forward our packets. There are different methods that it uses when it forwards its packets. We have process switching, fast switching, and Cisco Express forwarding. With process switching, an older packet forwarding mechanism, but it's still available for Cisco routers, so it's a legacy type of forwarding. Next, we have fast switching. It's common packet forwarding mechanism, which uses the fast switching cache to store the next hop information. When a packet arrives at your interface, it's forwarded to the control plane where the CPU searches for a match in the fast switching cache, or it's basically where it's looking to see if it's already found it before. If it's not there, it's process switched and forwarded to the exit interface, and the flow information for the packet is also stored into the fast switching cache so that it has it for future reference. If another packet's going to the same destination when it arrives at that interface, then it already knows the next hop information because it's just created it. With the Cisco Express forwarding, it's the most recent and preferred Cisco IOS packet forwarding mechanism. It's similar to fast switching in that it builds a forwarding information base, or the FIB, and an adjacency table. However, the table entries are not packet triggered. They're determined by changes in your topology when you add a new router. And then once the network has converged and all the routers have learned about this new router, then the FIB is updated so that it includes this new router, and the best path is determined from there. One of the ways to look at these three switching mechanisms is that process switching solves your problem by doing it longhand, and every time it sees the problem, it does it longhand, no matter if it's seen it once or 10 times. Fast switching solves the problem doing it longhand, but once it's learned it, it sticks it in its memory bank and uses it again. It doesn't go back and recreate the problem. With the Cisco Express forwarding, it goes ahead and figures out every possible best path determined by the different routers it has on its network, and it stores it in its FIB and uses it whenever the packet comes in. It's not having to process it. It already has that information.